Now let's move on to binary search. So binary search is a more efficient algorithm compared to linear search, which we've just looked at. However, there is one critical condition for binary search, and that is that the list must be sorted. So the list must be sorted when you're dealing with binary search. And how binary search basically works is that it is based on a divide and just write it somewhere here. It is based on a divide and conquer strategy. Yeah, so it is based on a divide and conquer strategy where instead of scanning each element one by one, like in linear search, it splits the search space in half with every comparison. So that dramatically reduces the number of steps required as you are looking through elements. So the key ideas in divide and conquer is that it focuses on the middle element of the array, and the middle element of the array is calculated halfway between the leftmost and the rightmost indices. So the leftmost index, and this is the rightmost index. And now for us to find the middle element, it's the element that is basically the middle or halfway between these two pointers. So we have a left and a right one. And when it comes to how we make decisions here, basically how we do that is, if the target value is equal to the middle element, then we have found our value, right? So the middle element has to be calculated. And how we would calculate a middle element is, we take basically halfway, we look for the halfway position between this. So here we have about 12 elements. So that divided by 2 becomes 6. So the element at index 6 is the middle element. And in this case, 5 here is going to be the middle index. Now, if this, assuming 5 was the target value, and if it is now, and it's now the middle element, when you're doing the comparisons, if this middle element is the element we're looking for, then that is the value we wanted. But if the target is less than the middle element, then the algorithm eliminates the right half of the array and focuses on the left half of the array. So if let's say the element that you're looking for was 3, and 5 is the middle element, we compare the two elements. And if you find that the element you're looking for is less than the middle element, then that means now we're going to discard this entire right half, and we focus on this. We focus on the left half. Then but now if the same case applies in the opposite, where if the element that we're looking for is greater than the middle element, then that means we discard the entire left half and focus on the entire right half, and we'll continue looking for a middle element at each part. So if this is the half that we're working with, we also look for the middle element here, and we continue that process until we get until we get the element that we're looking for. Now the repetition is going to continue. So basically the search space gets reduced to 0 when the target element is not found. So if the target element is not found, then the search space basically reduces to 0. As we've noticed, at each time, the problem size basically shrinks exponentially, and hence now why this has a time complexity of hence why it has a time complexity of O of n log n. So not n log n rather, but O of log n. That is the time complexity of this algorithm. So now that we've looked at some of these key concepts, rather some of these key areas in how it works, the key concepts here are basically it on this has to be the first thing that is met, which is that we make an assumption that, or rather, the array has to be sorted. So whenever you're starting to use binary search, the assumption is that the array is already sorted and it needs to be sorted. So which means that basically how that comes across is, because as you've noticed, the assumptions that we are making here is the left half is less than the target rather the middle element, and the right half is greater than the middle element. So ideally the array has to be sorted for that assumption to work. And this algorithm is highly efficient because, as you've seen, it takes O of n log n, O of n log n time. So, for example, if you have a data size of a data set rather of size n, then only log n comparisons are going to be required. So, if n was, let's say, if n was a million, so if you had a million elements, if that was the case, then it would take around 20 steps to look for the element that you want if you're using binary search, which shows you that it is highly efficient as opposed to linear search, where we'd have to go through the entire million elements. Yeah. So in terms of also efficiency, it is really, as you've seen, a million elements, a large data set, so which makes it suitable for large data sets. And this is the term complexity, and do note that the array needs to be sorted for this to work. So now we're going to try and basically go through this array that we have here and try to basically sort it. So we already understand in terms of indexing starts from 0 all the way. And to try and go ahead and basically look for an element here, let's assume that the element that we are looking for is 7. So 7 is the element that, this is our target element. How that is going to look like, we'll start with the left index. The leftmost index here is 0, and our right index is going to be 11. Remember, we have 12 elements all across. And we're going to calculate the middle index. And how we calculate the middle index, let me just get rid of this. So how we go ahead and okay, let me just delete this one more time. So how we calculate the middle, how we get the middle index, it's a simple formula. So to get the middle index, what you do is we're going to take the leftmost index, in this case, which is 0. Then we're going to add the rightmost index, which is 11, and we're going to find the floor of that. So, and which is going to give us 5. Now 5 is going to be the index 5 is going to be the middle element. So if you calculate here 0, 1, 2, 3, 4, 5, this 5 here becomes our 5 now becomes our middle. This becomes our middle index. And so of course we check their index, and then we know that 5, the element 5 is the what we're looking for. So we do the first comparison from here. We're going to compare 5 with the target element. In this case, our target element is 5. Once we do that comparison, we go ahead and realize that 7 is greater than 5. So 7 is greater than 5. And since that is the case, we're going to discard the left half. So this entire left half here is going to be discarded in that case. Then we'll now start working with the right half. Now what we do here is the middle index, we need to basically shift the left index. Remember, the left index initially was 0, but now that we've discarded the entire left half of this, what we need to shift the left index is going to be now mid plus 1. So the middle index, which is 5 here, we're going to do that middle index plus 1. So we just do mid plus 1. Mid plus 1 is going to be the middle index, and that brings us here. Rather, it's going to be the left index now. Then the second step is going to be now the right index still remains actually to be 11 as it is. Then we'll also calculate the middle index from here as well. So we're going to take what we have, in this case 6. Mid plus 1 is 6, so it's going to be 6. So okay, let's just edit on this. So it's going to be 6 plus 11. Then we find the floor of that, which gives us 8. So now the new mid index is going to be index 8. So this was 6, 7, 8, which is going to be 11. So now 11 here, 11 is our new mid. We compare this 11 with the target element, right? So once we compare, we find that 7 is less than 11. And if that is the case, that means we're going to go ahead and discard this entire right half. Then we're going to remain with only this section that we have here, because we're discarding actually even the 11. In the section that we're remaining with, where we have the left index. So the left index basically has to also, the left index has to basically sort of, it has to shift as well. So what we do from now, once we have found out, so this is the mid, and 11 year was the mid. We found that it was greater than. We discard this entire this other half that we have. Then that is going to leave us with 7, and it's going to leave us with 7 and 9. Then now what you do here is we're going to have the left index, as the left index is going to be 6. So this left index remains here, which is 5 plus 1, 6. Then the right index is going to be 7. So this right index already shifts to this point here. Now, how you get the right index? It's going to be the mid index minus 1, because we're now discarding this other side. Let's just write it here. So it's going to be mid index minus 1. That's how you get the right index. Then we also do a comparison now. So when you do a comparison, the middle element is going to be 7. Basically, trying to calculate the mid is going to be 6. So this will be 6 plus 7. Then finding the floor of this gives us 6 at the end. So 6 is going to be the middle element. Then we compare this element at index 6, and we find that that element is equivalent to 7. Hence, we have already found. Hence, if you do that, would have found our middle element. Not a middle element, rather, but the target element is found just like that. And I hope through all this rambling, you've been able to understand how binary search works and how to identify the right index, the left index, going all through until you get the right result that you're looking for. Again, do note that it's really key that you use the floor operator. It's going to help a lot in when it comes to how you should be using this. Yeah, the floor operator will get you the right index that you're looking for. Now we're going to go ahead and try and write the pseudocode for how you'd approach this, and you can go ahead and now implement that in a programming language of your choice, the one that you're a bit more comfortable with. So let's go ahead and write the pseudocode down here. I'll just call it pseudocode. And how we're going to do this is, let me use a different color for the pseudocode. Okay, so we have a function, of course. I'm going to create a function. So write the function how we do it in the programming language of your choice. And we're going to call it binary search. Binary search, and it needs two things. It needs the list of the array that we want to look for an element in. Then we also need the target element. And from there, the next thing that we need to do is we need to identify the left index and the right index. So the left index is going to be 0 for obvious reasons here, and the right index will now be the left, not left rather, but the length. It's going to be the length of the array minus 1, because indexing starts from 0. Then after this, what we're going to do is we're going to check. So while we're going to check basically here, while the left is less than or equal to the right, that is the case, we'll go ahead and find the middle element. So the middle element, you've seen how we do it. You check the left index, and then go ahead and have the right index minus the left index, and finally find the floor of this. So like that. Then what we'll do next is just with a number of if statements. So we're going to write a bunch of if statements basically. So I'm going to just check if the middle. Okay, let me just avoid using this to save on time. So we're going to check the array, that is the middle element. Then we check, we compare and see whether it meets it's equivalent to the target. If it's not equivalent to the target, we're going to return mid. Then we have an elif here, so an else if statement. So we're going to also check if the middle element, check if the middle element is less than the target. So if it is less than the target, as we've seen, we discard the entire right half. Then we're going to, that means we now shift the left, we shift the left index, which is going to be mid plus one. So that is if the array, that is the middle element is less than the target. So that means we discard the left half, not the right half. Then from here, the next thing we're going to do is just have an else block. And that is in case now the middle element is greater than the target. And then what you do is we need to shift the right index. Then the right index is going to, the rightmost index, that is going to be mid minus one. Else we're going to return negative one. We're going to return minus one. That is when the target is not found, basically. So it's when the target is not found. And with this pseudocode that we have here, you will be able to implement basically everything that you've implemented here, but now in the programming language of your choice. Just to go over this again, you need the leftmost index and the rightmost index, of course. Then you're going to check now, while the leftmost index is less than the rightmost index, less than or equal to, because remember, once the leftmost index is greater than, and that means you've already gone through the entire array or the entire list. So while this is true, you're going to look for the middle index, or the middle element, that is. Then you're going to check if that element is equivalent to the target, and then you're going to return it. Else if that middle element is less than the target, then that means you're going to discard the entire left half, then work with the entire with the right half. So that also means that you need to shift the left index. That is why we did this mid plus one here. You shift the left index. Else, if that's not the case, that is now if the middle element is greater than the target, then you go ahead and shift the right index, which is going to be mid minus one. Then finally, you're going to return negative one if a target is not found. That is after you've gone through the entire list that you're working with. And I do hope by now you've have the good understanding of what binary search is and how it works. Kindly, if you do have any questions, feel free to ask, and I'll be able to jump onto them and clarify everything for you. Thank you, and I'll see you on the next one.